Okay, all right, so let's get started. For today, the plan is we're going to go over one parameter model. Today is the gamma Poisson, so it is a conjugate situation. So we're going to look at what the density likelihood is, and then what the prior will be able to give, and then how to derive the posterior, and then look at various results. Okay, so that's the document that I posted on Moodle for that. And then after we're done with this, we're going to do a, I will prepare some supplementary material on multi-color approximation in general. We've been seeing this a lot so far until this point, but I have some other comments, general comments about it, so we're going to go over that. And then when we're done, the rest can be used for answering any questions you might have from Lab 2, as well as whatever homework questions that you have. Okay, so all right, so that's the agenda, and today we're going to start with this Poisson model. So it is actually covered in the textbook, so I encourage you to read it carefully, which is section 2 on this gamma Poisson, the Poisson model in general. So Poisson is a distribution that is commonly used to model count. So count, again, it's not continuous data anymore. So when you have counts, you probably won't be able to use normal. And then Poisson has one parameter. So let's look at the first one, the first part to start with. So Poisson, we're now using it as a density sampling distribution for the data, which, as you can see, has only one parameter. We call it theta. Sometimes you see lambda in other contexts, but it's the same. It's the same one parameter here. And then the density, as you can see, which is a discrete distribution. And you can see that the density for y equals to y is this theta, which is the unknown parameter raised to power of y. And then exponent negative theta divided by 1 factorial. Okay? And then the range of this random variable, as you can see, because it's about counts, can go from 0, can be 1, can be 2, go up to infinity. Okay? And then, of course, this unknown theta parameter actually going to control, say, we'll see later how like the range of y it will take, but overall you can take from 0, 1, 2, 3, all integer numbers up to infinity. One thing interesting about this Poisson distribution is you can see the property, mean, and the variance. It's both theta. Okay, so that's a feature of this Poisson distribution, that it has the same mean and variance. So that sort of, to some people, this will be a limitation of what you can do when you use Poisson as a data model. But a lot of times, like what we talked about earlier, Poisson is really ideal to model counts. So a lot of times people still use Poisson to model counts. So that's what we have. Okay? So that's for the data. And counts data can come up various ways. Say if you sit in the retreat and just count how many people come within a certain hour, and then that will be a Poisson distributed random variable. Or if you I don't know, just count how many courses people take on a given day, for example, all of those, as long as it counts, Poisson would be a suitable model for that. All right, so as we can see here, Poisson on the density, which only has one parameter, so this make Poisson a one parameter model, right? And then typical Bayesian inference framework, what we do is we're gonna give a prior, because we believe theta, the unknown parameter, is unknown and random. So you're going to give a prior distribution for this, and then you can do Bayesian inference either through simulation or through analytical solution. In this case, we are going to cover a conjugate prior choice for Poisson data, which again is the gamma distribution. So gamma, remember, we saw it last time when we were looking at say, if you have a normal sample, like normal data model, if you have the mean and the standard deviation, if you fix the mean, then the standard deviation, or we should say the precision, which is 1 over the variance, a gamma distribution will be a conjugate prior for that case. Okay, so the same gamma distribution we're talking about. So last time we sort of covered the PDF a little bit. And here I provide a little bit more information. As you can see, the gamma, the mean is A over B, the variance is A over B squared, and the mode is A minus B divided by B, depends on the values of A. Okay, so this, again, we did it, I think, in the lab. Yeah, in the first lab last week or the week before, that when we were trying to summarize the posterior for the beta binomial, remember that case? The question was asking you what would be the mean, what would be the mode, what would be the standard deviation of that beta posterior. So you can do various things. And for gamma as well, as you can see that if you know that the posterior distribution is a gamma distribution, then you can either just do the analytic solution, as you can see, as soon as you can derive the parameter A and B for the gamma posterior, then you can return the analytic solution of its mean, its variance, and then of course the standard deviation as well as the mode. Okay, so that's the analytic solution. And then you can also do a simulated solution. So that's what we've been using for multi-column approximation. If you know what A and B is, what you do is you simulate using R gamma in that case. You simulate large numbers of them. And then you can summarize the posterior mean, the variance, the mode. Like I said, there's no ready function in R to do that for you. But if you do a quick Google search, there are a lot of people wrote their own functions to return the mode, so you can use that. And those numbers you get from the simulation will be serving as approximation to the analytic solution. Okay, so again, we're gonna, like after this one parameter model for Poisson, we're gonna talk in detail about some other features of multi-column approximation again, but I do want to emphasize, yes, once we know the exact distribution for the prior, for the posterior, if you know what it is, you can use either the analytic solution or the multi-column approximation to summarize the posterior. Okay, so we've been talking about this multiple times now. All right, cool. So we were talking about using a gamma. I already said it. Gamma is actually a conjugate prior for Poisson data. So now I want you to actually complete. So I wrote down. So as you can see, this PDF document is just giving you blank space for you to derive. So I want you to do it in class as an exercise, and I put the steps for you. What the prior would be, so theta, we use pi theta. So this prior, as you can see, you should get the density from part 2, which is the gamma. And the likelihood, I asked you to complete the joint PDF. So again, we assume you observe a sequence of counts, okay? And then each is IID of the same Poisson, y theta, or like Poisson theta. So you should be able to write the joint PDF and then write it in terms of, I should add one more line here. Write it in terms of theta, which will be the likelihood. Okay, so remember, we always try to express the likelihood as a function of the unknown parameters, which is going to help you later to derive the posterior. Okay? And then lastly is the test of deriving the gamma posterior. I give the results here already, but I want you to derive it and then verify this result. Okay, so for today, don't worry too much about the normalizing constant. Just focus on whatever is in the kernel. Whatever like you find is can be considered as a constant in terms of theta, you can throw it into the proportional sign. So we're gonna pause for a few minutes, and then we're gonna come back together to look at this together. Okay? Okay, so here you can do the proportional. Just a quick hint that prior is from gamma distribution, so you can write whatever that you have from part 2. Make sure that express it in terms of theta. And then for the likelihood, you have to do the product of all of the Poisson density, which is from part 1. And because we're observing n of them, so it's a product of the joint, like the joint is the product of the marginal. And then once you get this pi theta and L theta, we know that Bayes' rule is following that the posterior is going to be proportional to the prior multiplies with the likelihood, right? And then the rest is making sure that you know what are constants. If they are, don't worry about them anymore. Throw them into the proportional sign and only keep the terms about theta. And then at the end of the day, you'll be able to recognize it as a gamma. And of course, you should refer back to the gamma density that we showed it up here to recognize what it is. Okay. So again, this, I think it's definitely easier than a normal case that we covered. Remember earlier last week, we covered using the normal prior for the mean of the normal, which was pretty involved because we need to get all of the square terms, like complete the square, etc. Here, I think it's less complicated, but make sure that you know how to do it. Okay, so take your time, talk to your neighbors, and I'll walk around to answer your question. So in this derivation exercise, you don't have to worry too much about the normalizing constant, but if you want to do it, just like what we did for the theta, you can do it afterwards. Feel free to do that. But for now, whatever that you can consider as constant for theta, you can throw it into the proportional sign and only focus on the terms about theta. Okay? Let's spend 2 more minutes on this. Okay, so I think most of you got it, but I do want to just do it really quick on the board because there are some common mistakes people make, and those, again, easy mistakes to make, so it'd be nice to keep in mind about them so later you don't getting to them again. So for the prior, you know it's going to be a gamma. You know it's a gamma. So for now, we'll keep writing the constant, but later on, you can throw it away. So it's theta raised to power a minus 1, and then in the, oh, I should have, okay, sorry. This is that notation. I will use this one for now. Okay. And that's for the prior. You pretty much just copy whatever you have. And then the likelihood needs some work because we have a joint PDF. So I will write on the first line first. So when you have the joint, it's good practice to express each one first and then keep the product outside. And then you can do it later, one by one. So what you have is you have theta raised to the power of yi. So this is the first mistake I saw many people make. So this is y1 to yn, each is iid. Okay, so you have a subscript of I for all of the observations. So you do have to keep that yi there. Okay, so it's yi, you got theta raised to the power of yi, and then this no I in there, so just keep in there. And then of course the factorial is also having the subscript. Okay. All right. So from here, a couple of things you can do. So really just do it step by step because again, in terms of theta and then in terms of the exponent function, the multiplication outside the product probably going to apply differently. So you just need to be careful, do it one by one. So I'm going to do this now for this step. So you're going to have the product. So let's keep in there. And then you're going to have the product. Some of you might skip those steps. That's fine. But I just want to make sure that we all get it right. So then this is the product of yi factorial. Okay. So the next step, just be careful. So for this part, it's theta raised to the power of yi, and then your product in all of them. Okay. So this is the same theta raised to different values of yi. So what you actually get, it's going to be theta raised to the power of sum of the yi. Okay. So this is algebra. Convince yourself this is true. Okay. So that's the first step. Then the second one, there's no I anymore in here. So we're merely just multiplying all of the exp negative theta. Okay? And then what that effect will be is negative n times theta in the exp. Okay? Some of you made the mistake of getting like the sum outside, etc., etc. So just be careful. All of this are should have covered in other classes before this one. So make sure that you get all of them. And then lastly, we're not going to deal with much of this, but I will keep writing it here. But again, let's see. Yeah. So this will be what the contribution of the posterior is. Right? And the next step is multiplying the prior and the posterior. Sorry, multiplying with the prior and the likelihood. Sorry, and then you'll be able to recognize what the posterior is. So since we start writing proportional sign, I will start throwing away constants. Right? So in the prior, whatever is not related to theta is constant. So this ratio is constant. Right? And then in the likelihood, whatever is not related to theta is also constant. So whatever the complicated product of all of those factorial can be considered as constant. So those two throw away. So what you have is theta raised to the power of a minus 1. And then in the exp negative b theta. And then from the likelihood, the sum of all of theta raised to the sum of yi. And then in the exponent negative n theta. Okay? So we have 4 terms related to theta, but they're of two forms, right? One is theta raised to some power. So this, you can write as equaling theta a plus sum of yi minus 1, and then exp negative b plus n theta. Okay, so we're almost there. This will be whatever terms that is related to theta. And then we already talked about this as a gamma conjugate. So recognize this to be the first parameters of the gamma distribution, and this is the second. Okay, you can look at it based on the gamma density that we show in part 2. Okay. So at the end of the day, you're going to have the posterior to be a gamma distribution with a plus sum of yi be the first, and b plus n to be the second parameter. Okay. Then you're done. Okay. So I would say, based on what I walked around, notice, first of all, definitely make sure that you have the yi, okay, because you do have the index of each likelihood. Okay. And then second is, when you're looking at joint PDF, like just do it really slowly. You don't have to worry, like don't rush. Like do it one by one. Make sure that you do every step correctly. And then thirdly, recognize what is constant, so you don't have to worry about them anymore. And in the end, of course, recognize which terms can be combined, and then from there, you should be able to recognize the posterior. Okay? Okay. Good. So this again is covered in the textbook. So if you have doubts or like not sure the details, you can go back to review that. And for this part, I just gonna this is just a summary of the results. That if you have the unknown parameter follows a gamma prior AB, and then all of the data IID Poisson, then the posterior for theta, which is the only unknown parameter, is this gamma. And one last thing I want to show is, we've been talking about this multiple times, of how to look at the posterior mean to be the weighted average of the prior and the sample mean. Okay, so we actually can see this again in this gamma Poisson conjugate example. So remember, at the beginning, I covered that the mean of a gamma distribution is A over B. Okay? So for this posterior distribution, gamma A plus sum of y and B plus n, the prior will just be the new A over the new B, right? So that's whatever we have here. And if you break it down, you can see that you get this prior mean. This is sample mean. Some people write it as y bar. That's fine as well. And then the weights associated. So the weight for the prior mean is B over B plus n. And the weights for the data mean is n over b plus n. Right? So n, again, is the sample size, right? And b, in this case, as you might guess, in the beta binomial conjugacy that we talked about before, in there, we thought about a plus b, which are the two parameters of the beta. We consider it, the sum of it, as the prior sample size, right? And we can see it in the derivation. And for this gamma conjugacy here, you can actually think of b as the prior sample size, as contrary to n, which is the data sample size, right? And then you can see as n increases, the data going to dominate, right? And of course, I mean, how it's going to dominate, we can do it through simulation and try with different values, like say different number of observations to see how it goes. But then at least in the form that we can see that we know as n increases, n over b plus n going to approach 0. And then the prior going to matter less and less as you collect more data. So this is another example. Okay. Lastly, you can also do prediction. In multicolor prediction, we know that if we want to make a new yi, for example, what we do, we first of all generate a new theta from its posterior, right? And then from that posterior theta draw, we can draw a new yi from the Poisson model. Okay, so step 1, theta from this gamma a plus sum of yi and b plus n. So this are all known. There's one a and b from the prior. Sum of yi and b and n there from the data. Okay, so you're gonna get a draw. So I'm gonna use like the little s as the upper script because we're usually gonna do multiple of them. Step 2 is you get a new y, which is we usually use tilde to represent the predicted value. And for that particular S index of this, you can draw it from a Poisson, right? And then the Poisson parameter will be the draw that you have previously in step 1. Okay. So when you do this, you're going to get a bunch of draws. So we typically use S, like capital S to be 1,000 of them. And usually we'll provide a good approximation. Sometimes you might want to even increase that number. So in the new homework, which is due next week, I added a question about experimenting with different sides of the simulations. And you can see, in general, the trend is as the larger the draws that you do, the better approximation of the simulated data, the simulated results to the analytic solution. Okay. Make sense? So this is, I mean, generically how you can do it, but then in practice, you have to write the code. But again, looking at this, probably not too complicated because gamma, you can use R gamma, right? And then Poisson is R pulse. Yeah, so you can search that, and then that's how you're gonna do the prediction. But then, of course, if you're asked to do posterior summary, then it's gonna be a bunch of R gamma, P gamma, D gamma, and Q gamma. Okay, it depends on the question. So now you can see that for all of the cases, except for the discrete that we saw at the beginning of this semester, for all of the conjugate cases that we have seen so far, that as long as you know what the posterior distribution is, you are able to summarize from both ways. Okay, analytic solution or the simulated solution. So regarding the simulated solutions, let's move to the second topic that we have for today.